Hello and welcome to the LUniverse Virtual Planetarium from Lancaster University. The following is a recording of one of our free live public shows that we ran during early 2021. I hope you enjoy.
So here is Andromeda. It is the closest galaxy to us and it's absolutely beautiful. It is one that you can observe at home as well if you have a nice little telescope. Truly stunning. So as a recap, what does a galaxy include? Well, galaxies are a massive collection of stars, gas clouds, planets, supernovas, nebulas, black holes, and dark matter. The core idea is that there are lots of stars orbiting a central supermassive black hole, just like that really good Muse song. And there is a large dark matter component which helps us to determine what a galaxy is. It's dark matter, like we discussed in the previous week, and maybe have a bit of discussion today, that helps give shape to galaxies and shape to our whole universe with the cosmic web. But when we're talking about galaxies, I cannot miss up on the opportunity to talk about genuinely my favourite image in all of astro, space, my degree, everything. My favourite image of all time. And it's this, at least a part of it, because it's quite a large image. This is the Hubble Ultra Deep Field. And this is the image taken by Hubble over an extended period of time, looking at one genuinely tiny part of our night sky. This image, the one that you're seeing here, is incredibly special because it was taken with one of Hubble's advanced cameras for surveys and the ultra wide camera from 2002 to 2012. So basically it's a combination of lots of images taken over that entire period, giving us one of the furthest views into the universe that we've ever managed to see. In here we have galaxies that exist not just in the visible light spectrum, so the stuff that we can see and interact with in our day-to-day life, but also in the infrared spectrum, or potentially some others as well. It is a large collection of galaxies right here, and I absolutely adore looking at this. It is such a stunning image, mostly because it gives us a chance to see just how big the scale of the universe actually is. And to do that, I'm going to use this cute little video provided to us by NASA and the European Space Agency. So this shows where that Hubble Ultra Deep Field is actually taken from in relation to another massive survey of galaxies. So that little square in the middle there was the Ultra Deep Field we were seeing with those hundreds and hundreds of galaxies visible in it. And already you can start to see how that is just a small, dark looking patch of another now seemingly dark looking patch in a cluster of bright galaxies. And the further we go out, we're seeing that even that cluster of galaxies also now looks like a tiny dark patch in another cluster of galaxies. And zooming all the way out here, we can see that that spot is just gone. We cannot see it whatsoever. How amazing is that? I absolutely love it. It's a really humbling reminder that, again, as I said last week, we can look up in the night sky and believe we understand everything, but the universe is always ready and willing to surprise us. The parts that look dark and have nothing in it are probably also brimming with galaxies and exciting space phenomena, and that is what we get to explore here. So with that, hopefully you've had a little opportunity to start writing in your questions and maybe inspired to ask some bits about galaxies as well. And without any further ado, I will pass over to Pascal to start asking some of your questions.
Thanks for that, Andrew. So the first question that we have is, what would happen if a black hole were to collapse or be eaten by another black hole?
Yeah, that's a great question. And thank you, Corvus and Lavinia, for asking that. So that definitely happens, actually. And that's not a sentence that I could have said, even 10 years ago, because it was something that's been theorized for a long time. So you have some black hole over here and some black hole over here, and they get close enough that they end up combining into a single black hole, and that's what happens. That is a process where they tend to orbit each other. They don't tend to just come in like straight head on. That doesn't really happen. But they tend to pass each other, and then they capture each other and they orbit. And what happens is, because black holes are such kind of they're so dense that they warp space around them, and you end up with two things that are warping space that are rotating around each other. You get this, there's some really cool animations of this online actually that you can look up, and you get this warping thing. It looks like waves. In fact, they are waves, but they're waves in space itself. So not like it's like a ripple in a pond kind of thing is the sort of thing that we use as an analogy, but it's not quite like that. It's like, well, the water is in the pond is creating the waves, but with a black hole, its space itself causes this rippling. And we detect those waves in the form of gravitational waves. And there are now instruments and detectors on Earth that can make those observations. So we can only see them for black holes that are like the size of stars, the mass of a single star, or 10 stars, that kind of thing now, because those are the instruments we have. But we're building instruments that can do that for supermassive black holes that have masses of like 1,000,000 times the mass of a single star. So what you get is that as they spiral in, the waves actually, they radiate energy out. And so the orbits keep shrinking and shrinking because they're losing energy to this gravitational radiation. And you get this spiraling in, and then eventually they come together, and there's this like quick moment, and it's called a chirp. Because if you translate the gravitational wave signal into sound, it sounds like whoop, and it makes this cool chirping sound. It's actually the ringtone in my phone was the first one that was ever discovered. So yeah, it's a really cool phenomenon and something that we first observed in 2015.
Okay, thank you very much for that. So the next question is, could there be more than one black hole in a galaxy?
Also an excellent question. Yeah, and the short answer is yes, there definitely are. So again, I mean, I study black holes, and I've studied black holes for a long time, but black holes for a long time were the sorts of things that we only looked at by the inference, by looking at their effect on other things. So for example, we know that the vast majority of galaxies have a supermassive black hole at their centers. And those black holes tend to be on their own, not entirely. And there are examples where we think we see sort of two black holes in the process, two supermassive black holes in the process of spiraling together, but both in the center of the galaxy. You could get that where you have, say, two galaxies that each have a black hole and they merge and they come together. And in the process of doing that, both of the supermassive black holes will themselves merge, because the black holes tend to be the heaviest things, the most massive things in their galaxy. And just as the way that gravity works, those two things both end up kind of at the center of what we call the gravitational potential, the center of mass of the galaxy. So when they both come to the center of mass, they end up merging. So it's certainly possible that a galaxy would have two supermassive black holes, but also black holes are the natural endpoint of the evolution of massive stars, and there are loads of massive stars in basically every galaxy, or remnants of massive stars. And so if the galaxy is old enough such that those massive stars have evolved to the end of their lives and become black holes, then you can have, hundreds easily. So there are different kinds of black holes in the sense that they're different masses. But yes, absolutely. I think probably it's a reasonable thing to say that almost every galaxy will have multiple black holes of varying masses.
Thank you. So next, Scarlett has asked, what is inside or beyond a black hole, and can you go through it?
Yeah, this is a question I get asked all the time, actually, when I give like public talks and things. And the answer is, I don't know. Actually, I think there is some research being done on this question, but I think this gets into a realm that I would call science fiction. And what I mean by that is, like, first-rate science fiction is really excellent and can be kind of excellent science in its way, because the difference between really good science fiction and really good science is just that you can't necessarily test science fiction, because black holes, once you get inside of a black hole, inside the event horizon of a black hole, we haven't discovered anything yet that can travel faster than light, and you have to travel faster than light if you're going to get out of a black hole, so nothing can escape. And so not even information can escape. Like if we were to send an astronaut or a robot or something inside of a black hole, I mean, if this were Interstellar or something, then they couldn't send the message back out to us about what was happening. right? So because it would just never reach us, because they would have to send something traveling the speed of light. That'd be the limit. So the answer is, I don't know. That's like a rigorous scientific answer. There's some theories about it. Sort of everything gets very compacted. In the very center, everything should be a singularity, which is like all of the mass is concentrated at one single point in space. As you're falling in, of course, it's very different. You kind of get stretched out because the tidal forces on a robot or something would be pretty extreme, and they would cause it to stretch out. That's called spaghettification. But the answer to what happens inside is going to be left to, for the moment, the domains of filmmakers and writers and philosophers of science.
Thank you. So next, Patrick has asked, what is Hawking radiation?
Yes, kind of a high-level technical scientific question. So Hawking radiation is named after Stephen Hawking, who theorized its existence for the first time. There's sort of a question about whether a black hole can give off energy or heat, whether that's possible. Some of the laws of thermodynamics suggest that it ought to be able to. And so the idea is that, I mean, how would you make that happen? Okay, so for that, we have to invoke quantum mechanics. And that is that at any given point in space, there is some chance at that point in space that spontaneously you can generate a pair of particles. And those pair of, like, you can't create or destroy energy, but you could kind of randomly fluctuate it. So what would happen is you would create, like, say, a neutrino and then an antineutrino, for example, or like an electron and then a positron. You would create them randomly, spontaneously, and they would be created really close to one another, and they would pretty much immediately annihilate each other. And so whatever energy would be, used in that creation would then go back into space. And so it's sort of a net zero transaction that this happens just sort of throughout the universe. However, if that happened right on the edge of the event horizon of a black hole, such that on one side you created one particle and on the other side you created the antiparticle, then one of them would fall into the black hole and one of them could escape. And then you actually do end up like creating energy, and that energy gets radiated away, which means that the black hole has to lose the energy because of conservation of energy. So that's what Hawking radiation is. It's an energy that gets radiated away by black holes. It's so minuscule that it's not the sort of thing we really expect to be able to detect from a black hole that we can observe, like, say, in my lifetime. I certainly wouldn't expect that to be like demonstrated in a lab or anything. It's the sort of thing that would become important when you're talking about really small black holes that might have formed in the very early universe. That could cause them to like evaporate, as it's called. But for like most black holes that we discuss in astrophysics, it's not a really important part, but it's theoretically really an important part of the understanding of black holes.
So following on from that, how do scientists calculate the mass of a black hole?
Yeah, that goes back to like what I mentioned a little bit earlier, I guess. This is something that I do pretty often. I could give you a very long answer to this, but I'll try to keep it short. So the basic answer is that we get the mass of the black hole if we're using not the gravitational wave thing, if we're looking at like the light that is given off by areas around the black hole, or looking at its influence on another star, because we'll see it in occasionally binary systems where there's a star orbiting what appears to be nothing, and we calculate just based on gravity what the mass of that thing has to be, and that's how we get the mass. And that's what we did with, say, the black hole that's in the center of the Milky Way. You can look at the orbits of the stars that just won the Nobel Prize, this discovery. You can look at the orbits of the stars and track them very carefully over time, and you can build up like a model of the gravity of the system. And you see that there is something that's like 10 million times the mass of the sun that this star is orbiting around. And there's one particular star that comes in on this like very elliptical orbit, and it comes in, it does this like whip around it, and it does this orbit. And so that really constrains the size of the thing that it's orbiting around. And so we know there's this really massive thing in this very small space. We know that it has to be a black hole, and we get a mass like measurement from that. The type of things that I do, I tend to look at like the spectrum of the light that's coming off. And so you break the light into its component wavelengths and look at how the intensity of the light varies with wavelength. And based on some of the properties of that, you can kind of infer what the mass has to be that you're orbiting around as well. And so there's various different ways to do it. And the gravitational wave is maybe the most direct in the sense that it's based on just a model of general relativity, and you observe what the chirp sound that you get, and you make a model of that, and it tells you what the two different masses had to be for that to happen. So there's lots of different ways to do it.
Thank you. So coming back to galaxies now, what happens when two galaxies collide?
Yeah, that's a good one. I actually study this, and I study the kind of corollary, which is I study how black holes grow when galaxies don't collide as well. Because so when two galaxies collide, let's imagine two Milky Way galaxies, right? So two big spiral galaxies, lovely, gorgeous structure that you can see. And those two galaxies collide, or the Milky Way and Andromeda. Those are good examples too. We think the Milky Way and Andromeda will eventually collide in several billion years. So you don't have to like change your retirement plans or anything. But when those two things collide, they basically massively disrupt one another. And so all of that nice structure of the spiral and everything that gets just torn apart, it's really gorgeous, really striking. There are some really beautiful astrophysical images that show mergers of galaxies. And what happens is everything gets churned up and mixed up. And the black holes will go to the center for the reasons I described below, before that you get the two massive things, they end up just slowly making their way, kind of migrating to the center. So the black holes will collide. What happens is the stars in the galaxies, generally, if you have two galaxies, like two Milky Ways, if they collided, stars are so far apart in galaxies that you can do this calculation. I have done this calculation to figure out how many stars you expect would collide because you feel like galaxies colliding is going to do something like this, right? Or maybe like they're going to collide and crash into one another and it's going to get all mixed up. But it's really so diffuse that in all likelihood, in the collision of two galaxies, no stars will collide. They just sort of pass right through one another. But the gas in the galaxies that the stars will be made from in the future, but hasn't been used to make stars yet, that does collide because that's more continuous. And so you get these big like shocked regions where they hit each other and they light up and they compress and then more stars form. It's a really cool process, really turbulent, lots of stuff happening. And you often end up taking material that falls down into the center of the galaxy, like gas material that can then get funneled down into the center, and then it falls onto the black holes and it spirals in and it heats up. And we call that an active galactic nucleus, or an AGN. So it's when lots of stuff is falling onto a black hole and it becomes very luminous. And in that circumstance, the black hole, which is normally, everybody thinks of a black hole as being a thing that, no light can escape from and stuff. But when you have that particular situation, the black hole can actually be much more luminous even than the entire galaxy, which is pretty cool. And that's actually what I study.
Thanks for that. It's a really great answer. So next up, DK asked, is there a physical limit to the size of a galaxy?
Okay, so I think there's probably a couple of limits to the size of a galaxy. So you have to answer that question by first answering the question, what is a galaxy? Which ought to be a simple, like everybody I think has an idea in their head of what counts as a galaxy. But if you try to like write down a definition, there's such a huge variety of galaxies out there. So there are galaxies that count as galaxies that have literally hundreds of stars. I think the smallest one that I know of has something like 140 stars in it. It's a little satellite galaxy of the Milky Way. And you can barely see it on, like, if you look at just an image of the sky and that galaxy is there. If I didn't tell you that galaxy is there, you'd just be like, I can't see it, because you don't see what you typically think of as a galaxy, you just see stars. But a galaxy has to have, it's not just stars, it has to have stars, it probably has gas. It doesn't have to have a black hole, but it does have to have dark matter. So if it doesn't have dark matter, then it's just a cluster of stars, right? So those two things, the fact that it has some stars and it has some dark matter, that kind of sets a little bit of a limit. So the smallest is probably limited by like how small you can make what's called the dark matter halo. So dark matter we actually don't know a lot about dark matter, but what we think we do know is that it doesn't behave. It's not like rocks or stars or planets. It's not big chunks. It's very, very small particles that are sort of similar to neutrinos. And neutrinos are hot and fast, and they don't collide with a lot of things, and so they kind of exist in a big fuzzy cloud. It's hard to get them very concentrated. So there's like a lower limit on the size of a dark matter halo, because that puts a limit on that, because basically it's sort of too energetic, and if it was too small and it couldn't hold itself together with gravity, it would fall apart. On the other side, on the most massive side, I don't think that there is really like a physical limit, but there is a limit that's set by how much time has elapsed. So the universe is like a little less than 14 billion years old. And just given like all the laws of physics and the conditions we see in the universe, there's only been so much time to build up mass in a galaxy. And so that kind of sets a limit on the biggest galaxies that we see. And those would have something like 1 trillion stars in them, maybe a little more. And then the dark matter is maybe 10 times bigger than that. And then in terms of physical size, you're just limited by the laws of physics. So like if you get a disk that's rotating, it can only get so big before it starts to tear itself apart. Those are the kind of limits that we talk about if we're talking about like the physical, like the radius of the galaxy or something. So there's a lot of different answers to that question. It's a really good question.
Thank you. So last week we touched on the different colours that galaxies can have. And so we've had a question, which is there any colour a galaxy cannot be beside black?
That's a great question, and it's one I'm going to have to think about for a second. So if you don't mind, I'm just going to talk you through this while I'm thinking out loud, okay? Okay, so like I said, galaxies are made of dark matter, which doesn't really impact the color because it's transparent to light, so that doesn't help anything. It doesn't radiate itself. But stars, right, and gas probably too, but really stars have to be in a galaxy for us to call it a galaxy. Otherwise, we just call it like a big nebula or something. So the thing about a star is that it radiates in a particular way. So for example, there are examples of how stars radiate that you can see on Earth. So like not so much a campfire like, but if you get a hot plate, right, and you plug in a hot plate or your electric hob or something, and it glows red, right? That red, that glow, is because it's very hot. And what happens when something like that gets very hot is it gives off some energy, and that energy has a particular spectrum. It has a particular distribution of how it's arranged across wavelengths. And the color can vary because the temperature varies, and that can change the shape of it, but the general shape doesn't change, just like where it's like how it's tilted and stuff changes, but that's about it. So if you wanted to have a galaxy that was, for example, like bright green, right, that's actually very hard to do, because green is like in the middle of the optical spectrum. And if you have something that's bright, that's emitting a lot of green light, it's probably also emitting a lot of blue light and a lot of red light. And so you end up with something that's a little bit closer, kind of whitish, right? That's not to say that green galaxies don't exist. There are galaxies that are actually called green peas. So those are galaxies that were discovered by Galaxy Zoo volunteers. They found these little compact galaxies that looked bright green on the images, and that's really unusual. And they worked out that it was because, so there are stars in those galaxies, definitely, but there's also a lot of gas in those galaxies. And gas, unlike stars, gas can emit kind of only at particular wavelengths, depending on how hot it is and some other things about it and what it's made of and stuff. And this gas was heated to just the right temperature where it was giving off a ton of light along this one wavelength. That's a wavelength given off by oxygen atoms, not molecules, atoms. And it's ionized oxygen, and that it is 5,000 angstroms or 500 nanometers, which is right in the middle of green. And so the galaxy looked green because of that. So that can happen, but that would be very hard to get. And it's only in certain circumstances. So I guess, yeah, no, there's not really any color it couldn't be. There's just some colors that are much, much rarer than others, I would say.
Thank you. So going back to galaxy collisions, Holly asked, how often do galaxies collide, and how close was the last one to happen to us?
Oh, okay, wow, that's a great question too. So how often do galaxies collide is not often, usually, probably is the short answer, but so a galaxy over the course of its lifetime will probably have had some collision. Like I said, so the universe is a little less than 14 billion years old. 14 billion years is a long time. And you have to imagine, so at the beginning of the universe, like early on, not at like time 0, but like let's say time 1 billion years, which is enough time for the kind of general gas of the like particles, plasma in the universe to kind of coalesce and start to actually form the things that we think of as being required for galaxies, so stars and dark matter and gas and so on. And that happens. Okay, so we have 12 billion years to evolve, but at that time, at a billion years, the universe was a lot smaller. And a lot denser and a lot hotter. And so stuff was just a lot closer together. And so that's pretty much how you built up galaxies. You would start with like a smallish cloud and it would collide with another cloud, and then you'd have one that was twice as big. And so that's how you grow galaxies. And so that just always happened with collisions. And then as the universe expands, that becomes less and less common, but how common it is for any one galaxy depends on where you are, because there are parts of the universe that are really, really like dense, that have got lots of stuff in them. Like you can see images of clusters of galaxies, and those are, you might have 1,000 galaxies all orbiting each other in this quite complex thing. And there's a lot of collisions in those. But you might also have areas where there are like voids. And those voids where you might have one galaxy and then nothing for millions or billions of light years. And those obviously don't collide very often. So then it really, after you get to a certain kind of age of the universe, which is probably about halfway, then it really, really depends on where you are, how often you have a collision if you're a particular galaxy. And in terms of us, so the other question that's sort of implied in the like how often do galaxies collide is, I gave the example of a galaxy colliding with another galaxy of the same size. But that actually is maybe the least common, because what's much more likely is that you have a galaxy like the Milky Way, and then a smaller galaxy that we would call like a satellite galaxy or like a dwarf galaxy that might be, you know, 1/10 of the size or even 100th of the size. And that probably happens pretty frequently. So it actually hasn't been that long since the Milky Way kind of ate a satellite galaxy. And we know from looking at the detailed orbits of the stars that are not in the disk of the galaxy, but are in the kind of extended cloud, which we call the halo of the galaxy. We know from looking at details of the orbits there that there have been several of those collisions over the past several billion years. So it's quite a complex answer, but it's really cool to watch that as we discover more about it.
Thank you. So going more towards black holes again, are there any probes being sent towards the center of our galaxy and the black hole there?
So by probes, I think that probably means like actual physical probes, like if it was Star Trek. So then in that case, the answer is no. There's a lot of observations being done. Certainly, I think, so there's an experiment called LISA that is a gravitational wave detector that's going to be in space. It's not going to be for a while now because they're still building it and developing the technology. And that will help us look at black holes like the one in our galaxy, although I don't think our galaxies, I don't think what we call it Sagittarius A star, because sort of the constellation it's in. And anyway, that black hole isn't going to collide with another black hole, we think, although there might be one. Anyway, we don't know. That's still open to details. But if there is a collision, Lisa might be able to see that, and Lisa will be able to see others. But in terms of looking at our own galaxy, it's right now pretty much what we do is we just sort of wait for the information to come to us, and then we build instruments either in space around our planet or on the ground that can receive that information. So it's kind of passive. We haven't really sent out probes anywhere except the solar system and just beyond with Voyager. But that's not really, I mean, the fact that Voyager got out that far is wonderful, and that was its intent, but it's not headed toward the center of the galaxy or anything. I really am hoping for like a Star Trek-like future where we can send a probe off and just like go and look and see what's there. But I think we have a long way to go to get to the center of the galaxy. I think maybe the first thing we'd want to do would be to like send a probe to our nearest star, Proxima Centauri, which may have a planet around it. And if that's the case, we'd love to take a picture of that and get a sense of that as well.
Thank you. So that leads quite nicely into our next question, which is how do we take pictures of black holes if photons can't escape a black hole's gravitational influence?
Yeah, that's a really good question. And it is a little non-intuitive, right? Because I'm talking about detecting black holes and all of that, and you're like, but we can't actually see the black hole itself. And that's true. But we can observe what's going on around the black hole. So for the black holes that I look at, the supermassive black holes that are in the centers of galaxies, there's lots of other stuff in the centers of galaxies. And some of that will fall toward the black hole over time with gravity. And as that happens, it will, as I said, it usually doesn't fall head on. It usually falls and then sort of ends up orbiting, and it spirals in. And as that falls in, it's not what's usually orbiting around is there might be some stars, but at the very center there'll be like gas and just material, and that is stuff that can collide with itself, like it can collide with other gas, and it can, so it heats up with friction and with magnetic effects, and that heating of that as it falls toward the black hole, that causes it to radiate. And we observe that radiation. But all of this happens before it actually crosses the event horizon. So there is a point, like when we make a model of a black hole, or I could draw you a cartoon picture of what that looks like. And it's basically like there's kind of a big gas cloud. It might be like a ring because a lot of it's orbiting, and so it's rotating, so it gets kind of flattened. And then as you get closer to it, it's orbiting faster, so it gets even flatter. And then there's a very thin disk as it's orbiting. And then right in the center of that disk, there's just a big hole. Because at some point stuff just starts to fall in, and then it goes past the event horizon and we just can't see it at all. So we can't directly observe it. The closest we could get is like the picture with the Event Horizon Telescope, which sort of directly imaged the black hole. But even then, they didn't say it directly imaged the black hole. What they said is that it imaged the shadow of the black hole, because they were able to take an image in the radio of that region where the stuff is falling in and see the hole directly, that black area where we couldn't see anything else. And so that's the closest we can really get, and we'll probably ever be able to get, I guess.
That's great. Thank you very much. So next, how big is the biggest black hole that we've ever found?
Okay, this is like a trivia question, like in a pub quiz when I get this right. Expert on black holes. I don't know the exact number, but the biggest that we've ever found is about 10 billion times the mass of the sun. About. So if you were putting that in scientific notation, you would have a 10 to the 10. It's a big number. And so that is in a relatively nearby galaxy. A big galaxy, and it's like a huge elliptical galaxy, and that's the biggest we've seen. But we think it's possible that black holes might exist that are bigger than that. It's just that probably they are very rare, because for the same reason that galaxies that are that big are really rare, there just sort of hasn't been time to build up to the huge, like, get bigger galaxies than that. Same is true of black holes. Like, the universe is only so long, which is a long time. 14 billion years is a long time, but it's still probably not enough time that even bigger galaxies, even bigger black holes haven't really had a chance to grow to that point yet. And so probably if there is a, like, 100 billion times the mass of a star, if that exists somewhere, it might be that it's just so far away that we haven't been able to detect it yet, because that type of thing ought to be pretty rare.
Thank you. So we had a question last week, which I just wanted to bring back because it was a good question and we couldn't really answer it properly at the time, which was, what formed first, the galaxy or the black hole?
Oh, I love this question. This is an active area of research, the chicken or the egg. It's a really, really good question. And I suspect the answer is both, which is, I'm not trying to get out of answering the question, but what I mean is that the universe is a complex place. So there's lots of research being done on how you form black holes the first time, like in the very early universe. We know how it happens today, right? So we know that you can form a black hole from a star, right? A very massive star reaches the end point of its evolution, it explodes, and it leaves behind a black hole as a remnant, which is some fraction of the mass of the star. But okay, so that probably can happen in the very early universe, but actually stars themselves were very different. The very first generation of stars was very different in the early universe. And that's because the universe itself didn't have as many of the heavier elements, so the stars just evolved a little bit differently. And what's more important to this is that they formed at higher masses in general. So you could have a much bigger star that would end up making a much bigger black hole. So in theory, in that particular case, you would have to form the star first and then have the black hole evolve. So sort of if we're defining a galaxy as a thing that has at least one star and a dark matter halo, which was everywhere in the early universe, that would mean the galaxy formed first. However, it's also possible, we think, this would not be possible today, but we think it's possible in the early universe, that you could just go, like you could have a cloud of things that would normally collapse to form a star, this like cloud of gas, or many stars, because it would like fragment and then you get lots of stars forming all at once. We think it's possible in the very early universe that you could have that cloud be just so big and collapse all like as a whole thing that it just never went through the star phase and just goes whoop and goes straight into a black hole. And that's called a direct collapse black hole. And those probably, well, we haven't found any reason they can't form. And the universe is a complex place. And the laws of physics kind of work such that if something isn't explicitly forbidden, it's probably happening somewhere in the universe at some point. So it's probably the case that there are situations where you get a direct collapse black hole, and that's the first thing to form. And then stars might form around it from residual gas, and then the black hole forms first. And there are probably other cases where the galaxy formed first. So that's why my answer is both.
Well, Brooke, thank you ever so much for your fantastic answers, especially on that last one there. That was really interesting and a much more cohesive answer than I managed to give. Brilliant. I was actually behind the scenes doing lots of little bits and bobs, and multiple times I just stopped and just sat there like this. It's like, it was really interesting. I learned so much. So thank you so much for coming. So as your lovely feedback rolls in, I must say first a massive thank you to Pascal, who once again did such a great job moderating and asking all the questions. Hey, Pascal.
Thanks,
and
guys.
a massive thank you to Dr. Brooke Simmons, who answered the questions beautifully.
They were great
Thanks so
questions.
much, Brooke. It was genuinely lovely to have you here, and thank you so much for giving up time in your busy schedule.
Thank you for watching, and I hope you enjoyed learning a little more about our amazing universe. Our team from Lancaster University also runs shows for schools, community groups and more, both in person with our portable inflatable planetarium and online. But any in-person events are subject to current COVID restrictions. If you're a teacher, community group leader or part of a similar educational organisation, please do get in touch. We're particularly keen to make connections with those in our region of Lancashire and Cumbria, but we'd love to hear from you wherever you are. But for now, take care and keep learning more about the amazing wonders of our night sky. Thank you.